Okay, hello. Today we're going to be going over what binary search is. So, first of all, what is it? So, it is a search algorithm. And it takes a sorted array. And it looks for a particular value. And each time it does that, um, it has the problem space. Um, so it basically makes smaller and smaller arrays until it finds the key, or if it doesn't, then it just exits. It just exits without finding the key. So how does this work? So say we have a sorted array. So 2, 7, 23, 34, 36, 54, 61, and 83. Um, the size of the size of this array is 8, and the number we are looking for, our key, that is 23. So to start off with, we are going to set our pointers. So for binary search, we start with our left pointer. It starts all the way at the far left side, so it always starts at index 0. And on the right side, we have our right pointer, which always starts off pointing at the very uh, end of the array we are searching. So we are at index 7 because that is the last index in our array. And next we have to calculate the midpoint of this array. So we do that by, the formula for this is the value of the left pointer plus the value of the right pointer divided by 2. So in this case, we have 0 plus 7, and that's 8.5. We don't have an index of 3.5. That's not possible. So you can either round up or round down. I'm rounding up because that makes sense to me. So this is our mid. This is our midpoint, but we can call it mid for short. So we check the value that's at that midpoint. So at our index of 4, the value there is 36. So now we make a comparison. So 36 is greater than 23. Who knew? So we have to decide what half of the array we need to look at. So since we found out that 36 is greater than 23, we know we can eliminate half, the upper half of the array. We don't need to look there anymore because it's impossible that our key would be there since this is a sorted array. So we only need to look at the lower half. So we set our j to the new endpoint of our subarray. So j is now set to the value of mid minus 1. So it is now at 3. So at our new array, we are looking at 2, 7, 23, and 34. And we keep up this process until we find our key. So we calculate a new midpoint. So our left, oh, J, that's also a right point. You can call it how you want. This is just how I call it's called in the code I have. Sorry about that. So um our left pointer is still at 0. Our right pointer is now at 3. Divide that by 2. That's 1.5. Let's round that up to 2. This is our new mid. So we take a look at the value at index 2, 23. Now we compare that to our key. Now I don't know if y'all know this, but 23 is equal to 23. So we have found the index at which our value is at. So key is at, yeah. So we found it. You know where it is. Now let me show you the code for this. So this is quite a lot. So first we have a sorted array we use. It has to be sorted because that's how we determine whether or not our key is somewhere or not. Like if it's not sorted, if it's all jumbled all over the place, then this won't work. It's not gonna work. And then we have the key we're looking for. And then we have our left pointer and our right pointer. And there's only really one method to this. It's just the binary search method itself. It's recursive, so it calls itself again and again and again until it's at a point where you can't really split things in half anymore. So if the left pointer is greater than the right pointer, that means you're at a point where you can't split the array in half anymore. So you have to stop at that point. Y'all can read this further in depth on your own time. Because now I'm gonna be moving on to time complexity. So for time complexity, let's start with the average case. So what do we know about binary search? Well, you split the array in half until one element remains, or up to until one element remains if you don't find your key beforehand. So you start with an array of n, you split that in half, you split that half in half, and then you split that in half again. And you keep going and going. You keep splitting the sample space smaller and smaller and smaller until you only have one element left standing. So let's say k is the number of halvings you have. Number of halvings. So we want k when there's only one element left. We want to find out what k is. So we can make a little formula for this. So n over 2k equals 1. And now we have to solve for k. So you can move this up here. N equals 2k. Now we want to get this k by itself. but it's stuck up here. Now, how do we do that? Well, we can use a log on both sides. So log 2n equals 2. We're using base 2 because like this will cancel this 2 out. And this will bring the k by itself. It'll just be a regular variable. I don't know if I explained that well, but math is not my main thing, so yeah. So we can cancel this. So at the end, you have log base 2 of n equals k. So this is the total number of steps that binary search has to go through before it can before it finds its key, basically. And the work per step is constant. It has a O of 1 time complexity because you're not really doing too much outside of having it. You're just like making a comparison about like what you should. You're just making a comparison and seeing whether you should go to the upper half or lower half to continue your search. So therefore, for the average case, you have an O of log n time complexity. And when would the average case be? I don't know. It's basically just searching for a key and it's not at first or last comparison. I think that's the best way to describe that. Oh. And it's also in the array. So for best case, so the best case on your first comparison, value at index mid equals to key. That's one comparison. So the time complexity is O of 1. It's constant. You only had to do one step. You didn't have to go log of n steps to find it, so that's why it's this time complexity. So for the worst case, it's either the key is not there, or the key is in the last place checked. So both of these, you'll have to do like the max number of steps. But as we found out earlier, this max number of steps is log n. So the time complexity is still O of log n. And that about wraps it up for binary search. Yeah. Thank you.